Okay, now we're going to go over single replacement reactions. Single replacement reactions have to do with, will a metal or nonmetal replace another metal or nonmetal in a reaction? For this, we actually have an activity series, and this is kind of the ranking of metals in terms of who's the best metal versus who's the worst metal. So, the first thing you want to do is you want to look at what you've got. We have Na that has a 1 plus charge. We have Mg that has a 2 plus charge. We have chlorine that has a 1 minus charge. Now, if you look at your activity series, here's Na and here's Mg. Sodium is the quote unquote better metal because it is higher on the list. So chlorine is going to leave magnesium and go on over to sodium. So our products are going to be Na1 plus, Cl1 minus, plus Mg2 plus. Our final equation will look like this when you crisscross the charges. Whoops, NaCl plus magnesium. Okay, now we need to balance it. 1 Na, 1 Na, 1 Mg, 1 Mg, 2 Cl's, so we need to put 2 in front of sodium chloride. And then because we doubled the sodium, we need to double the sodium on the reactant side. Now that's a balanced equation. But what if we reversed it? Magnesium is going to try to steal chlorine from sodium, but magnesium is lower, so it can't happen. In that case, on your assignments and in real life, you would say no reaction because magnesium couldn't replace sodium because magnesium is quote unquote worse than sodium. Now let's look at this one. Calcium and silver. Calcium is all the way at the bottom, or excuse me, calcium's here, silver's all the way at the bottom. Now notice that these three at the bottom are silver, platinum, and gold. Those are three of the metals that are most jewelry is made out of. The reason that jewelry is made out of these metals is because they're not reactive, which means they don't turn your skin green when you put on a ring and so forth. That's why we make most of our metals or most of our jewelry out of those metals because they don't react. So here, the calcium is going to react because it's going to take the place of the silver. So our products are going to be CaCl, Ca2 plus, Cal1 minus, and Ag1 plus. That gives us a final reaction of CaCl2 plus Ag. Now we need to balance it. 1 calcium, 1 calcium, 1 silver, 1 silver, 1 chlorine, 2 chlorine. We got to double the silver chloride, which means that we have to double the silver over here. And now that reaction is balanced. Can Ag or can silver steal chlorine from calcium? Silver's all the way down here, calcium's all the way up here. Lower metals cannot take from higher metals. So this again would be a no reaction. Now, it doesn't always have to be the metals that are replacing. You can replace the anions. So in this case, the fluorine, H plus, and chlorine. You'll look at the activity series of the halogens. This is the same order that they're listed in on the periodic table. So we know that fluorine wants to take everything more than any other halogen. We're comparing fluorine and chlorine in this. Fluorine is higher, so the hydrogen is going to go to the fluorine. But we also know that when you write chlorine, it's a halogen. So just like you see that F2, you have to put Cl2 because it's one of the diatomic molecules. So now let's balance the reaction. 2 fluorine, 2 fluorine, 1 hydrogen, 2 hydrogen, 2 chlorine, 2 chlorine. All balanced. Can the reverse reaction happen? You have fluorine and chlorine. Will H leave fluorine to go to chlorine? Well, it's not ever going to downgrade. So this again would be no reaction. And that's how you use the activity series of metals and nonmetals to predict products for single replacement reactions.